welcome to T Academy. From today onwards, we'll be starting a series of lectures on transmission lines. In my opinion, this is one of the most difficult topics to comprehend in high speed signal designs, and I have seen people struggle with this because they don't truly understand the transmission line nature of interconnects, especially when it comes to high speed signal designs. So that's why I wanted to show a bit of theory in this first class and one simple simulation that will demonstrate that how the output voltage at the far end of an interconnect can be higher than what we launch into the transmission line. So for this, I'll use a very simple setup where I have a driver which launches a 1 volt signal. So the output of this driver is this 1 volt signal which is launched over this transmission line. So this could be anything. It could be a trace on a PCB, it could be a coax cable. So this is a transmission line, and a transmission line is characterized by two main parameters. One is the characteristic impedance, usually taken as 50 ohm. There's no hard and fast rule, but let's assume that this is 50 ohms, and a time delay. So let's assume the time delay here is 1 nanosecond. So this 1 volt signal will take 1 nanosecond to reach the far end of this transmission line. And let's assume that the transmission line is an open circuit at the end. That means it is not connected to ground. Now we are interested in finding out the voltage at this far end of the transmission line. First we will find out theoretically what this voltage would look like, and then we'll do a simulation in SPICE to verify our results. So this driver can be represented as a voltage source. So it is outputting a 1 volt signal, and all drivers have some sort of source impedance. So let's assume that the source impedance of this driver is 10 ohms. Now when this 1 volt signal approaches this transmission line, it sees an impedance looking into the transmission line which is equal to the characteristic impedance. So in essence, this is making a voltage divider. So this is the characteristic impedance Z0 of 50 ohms, and the signal that is launched into the transmission line is what appears across this characteristic impedance. So let's call this V incident. So in order to calculate, we just use the voltage divider formula to find out the voltage across Z0, which would be 50 divided by 50 plus 10, which will be 60 times 1 volt, and this gives an output of 0.84 volts. So the actual signal launched into the transmission line is 0.84 volts. So let's see what happens a nanosecond later when this 0.84 volt pulse reaches the far end. So here at t equal to 1 nanosecond, which is the delay time of the transmission line, this 0.84 volt signal will reach the far end, and here, looking towards its output, it sees an open circuit. So there is no other way for the voltage to go. Therefore, this voltage will reflect back into the transmission line. So at the output, what we will have is a mirror image of this incident voltage, which will reflect back onto the transmission line. Now, why this occurs, we will derive using the concepts of reflection coefficient in the upcoming lecture. So this 0.84 volt pulse will be reflected back onto the transmission line, which we will call V reflected. So this one here was the incident voltage onto the transmission line, 0.84 volt, and now we have another reflected voltage of 0.84 volt, which will travel in the opposite direction. And a nanosecond later, this reflected voltage will hit the driver transmission line interconnect, and then based on the source impedance and the characteristic impedance, a part of this reflected wave will reflect again into the transmission line. In an upcoming lecture, we will make a bounce diagram which will capture all these transmissions and reflections at the different boundaries. In today's lecture, we just want to simulate the output voltage at the far end. And this we can simply do in SPICE by connecting a voltage probe at the far end of the transmission line. Voltage probe is connected between the far end and ground. What it will measure would be V total, which will be the sum of the incident voltage and the reflected voltage, and we will measure 1.68 volts, even though we launched a signal of 1 volt onto the transmission line. So how can this happen? This we'll learn in an upcoming lecture. This is because the transmission line can be approximated by LC resonant banks, and it is the internal resonance of this LC circuit that causes the output voltage to become greater than the voltage that is launched into the transmission line. So let's now go to SPICE and visualize this output voltage with a simulation. So now we will be simulating this transmission line using LTSpice. So first I will be adding this transmission line. I'll right click to select the time delay as 1 nanosecond, and I'll keep the characteristic impedance as it is. Then I'll be placing a voltage source here. I'll right click and go to advanced and select pulse with an initial voltage of 0 volt and on voltage of 1 volt. A rise time which I'll put much lower than the time delay, and let's put T on as 10 nanoseconds. So this is the pulsed input voltage. Next I want to put a source resistance which will act as the resistance of the driver, and our analysis we used it as 10 ohms. Let's connect all this together. And this far end of the transmission line, I will keep it as open, since we want the incident voltage to reflect from the open end of the transmission line. The only thing missing is a ground connection at the output, and I'll label this output voltage as V far. so which is the voltage we are interested in probing. So that's all. Let's go ahead and simulate it for 10 nanoseconds, which are 10 time delays. And I'll put my probe at this far end to come up with this beautiful output voltage waveform, where you can readily see that the launched input voltage reaches the far end after 1 nanosecond, which is the time delay of the transmission line. And here, if I were to put a cursor, you'll see that the output voltage is very close to what we found out, 1.66 volt, which is the sum of the incident voltage as well as the reflected voltage from this open far end of the transmission line. So in an upcoming lecture, we'll see all the reflections that are occurring at the source side as well as at the far end of the transmission line. So for instance, this reflection is occurring at the source transmission line interconnect, and we will introduce the concept of reflection coefficient to construct bounce diagrams, and this will greatly help us in understanding the transmission line behavior of high-speed interconnects. So that's it for today's lecture. I hope it was useful. Please subscribe to my channel if you like the content, and if you want some lecture on a particular topic, please let me know in the comment section.